Hello students. So today we are on to the last lecture of the batteries. Till now we have discussed about the basic concepts of battery, its classification, its history, various examples of primary and secondary batteries, and also fuel cells in brief. For today's lecture we will be discussing about some basic concepts of fuel cells, then principle of the fuel cell with classification of the fuel cells in detail, then fuel cell setup and its efficiency, solar cell and PV cell, that is photovoltaic cell, then photovoltaic effect, and also the solar polymer cell. So let's start with the basics of the fuel cells. Fuel cell is a galvanic cell which combines hydrogen and oxygen to produce electricity. The core of each fuel cell consists of an electrolyte and two electrodes, and the negative electrode of fuel such as hydrogen is being oxidized, whereas at the positive cathode, that is the positive electrode, oxygen is reduced. So we can say ions are transported through the electrolytic membrane or electrolytic solution from one side to the other. The type of this electrolytic membrane or solution determines the temperature window of this particular operation of fuel cell. This window of operation in turn determines the catalyst that can be used and the purity of the fuel to be used. So we can say the classification of the fuel cells are based on the temperature and the electrolytic solution and also the fuel which we are using in that particular fuel cell and for the catalyst also. The theoretical open circuit voltage of a hydrogen oxygen fuel cell is 1.23 volts at 298 Kelvin, but in actual it is around 1 volt at open circuit, and also under the load conditions the cell voltage can be 0.5 to 0.8 volts, that is we can say it is decreased to 0.5 to 0.8 in actual practice under the load conditions, whereas theoretical we can say that we are having 1.23 volts of the circuit voltage. As hydrogen ions are released from the anodic material, these ions act as current passage which can be used as a load. Now the classification of the fuel cells. All 6 types of fuel cells are as follows. First, the proton exchange membrane fuel cell, then direct methanol fuel cell, phosphoric acid fuel cell, alkaline fuel cell, solid oxide fuel cell, and the last molten carbonate fuel cell. So let's start with the first type of fuel cell, that is the proton exchange membrane fuel cell. As the name suggests, the membrane. So we are using water based acidic polymer membrane in this particular type of fuel cells, and hence its name is polymer electrolytic membrane fuel cell. It's also using platinum based catalyst and on both the electrodes, which is highly costly. So we can say it is hydrogen fueled and very costly fuel cell. These type of fuel cells are operated at particularly low temperatures, mainly below 100 degrees Celsius. And the high temperature variants of these fuel cells use a mineral acid based electrolyte, and that can be operated up till 200 degrees Celsius of temperature. The electrical output can be varied and hence ideal for vehicles. Now the next type of fuel cell is direct methanol fuel cell. As the name suggests, the fuel which we are using in this type of fuel cell is methanol, and the electrolytic membrane is again a polymer type of membrane like in PEMFC, that is in proton exchange membrane fuel cell. And in this type of fuel cells the catalyst used is platinum ruthenium combination for anode, and whereas only platinum catalyst for the cathode. These type of catalysts can draw hydrogen atoms from liquid methanol, which is acting as a fuel and giving the cell its name, that is the direct methanol. These are operated at temperature range of 60 degrees Celsius till 130 degrees Celsius temperature. These type of fuel cells are convenient for portable power applications with outputs generally less than 250 watt like in battery chargers or in laptops. Now the next type, that is the phosphoric acid fuel cell. As the name suggests, again the electrolytic solution is of phosphoric acid in a bonded silicon carbide matrix. These fuel cells use a finely dispersed platinum catalyst on carbon, and they are quite resistant to poisoning by carbon monoxide. These type of fuel cells are operated at a range of around 180 degrees Celsius of temperature, whereas the electrical efficiency is relatively low of these fuel cells, but the overall efficiency can be over 80% if the heat is used. So these type of fuel cells are generally used in stationary power generators for 100 kilowatt to 400 kilowatt of power. Now the next type, alkaline fuel cell. As the name suggests, again the electrolytic solution or electrolytic membrane should be alkaline. So we are using potassium hydroxide mixed in water as an electrolytic solution for these particular fuel cells. These fuel cells generally use a nickel catalyst on both the electrodes, and they are fueled with pure hydrogen and oxygen, as they are very sensitive to poisoning when exposed to carbon dioxide. As we have seen that in fuel cells generally we put air as an oxygen fuel, but particularly in alkaline fuel cells we generally, or we can say mostly, we use only oxygen, pure oxygen instead of air, so that it cannot be exposed to carbon dioxide and hence it can't be poisoning. The typical operating temperature range for these alkaline fuel cells is around 70 degrees Celsius and hence can offer high electrical efficiency. These fuel cells tend to have relatively large footprints and hence used on NASA shuttles throughout the space program. Now the next type of fuel cell is solid oxide fuel cell. Again, as the name suggests, the electrolytic solution will be solid. So it is using solid ceramic such as stabilized zirconium oxide as an electrolytic membrane for these particular fuel cells. And in these type of fuel cells, a precious metal catalyst is not necessary. They can run on hydrocarbon fuels such as methane, and these are highest temperature fuel cells and hence can operate till 1000 degrees Celsius of temperature. These fuel cells best run continuously due to the high operating temperature, and hence the temperature, as I have already discussed, that it is around 800 to 1000 degrees Celsius, and hence they are popular in stationary power generation. Now the last type of fuel cell is molten carbonate fuel cell. Again, the electrolytic membrane is using the molten carbonate salt suspended in a porous ceramic matrix. Again, in these type of fuel cells, it is not necessary that we are using precious metal as a catalyst. These can run on hydrocarbon fuels, again like example methane. They can operate at around 650 degrees Celsius of temperature. These are best run continuously due to the high operating temperature range. Most fuel cell power plants of megawatt capacity use molten carbonate fuel cells, as do large combined heat and power plants, because these fuel cells operate at very high range as well as they can give high efficiency of megawatt power. Now the fuel cell setup. As we have seen, the fuel cell is consisting of electrodes and electrolytic solution, whereas we are giving fuel, that is hydrogen and oxygen, as per the limitation of that fuel cell, or we can say on the basis of the application. When we are using the fuel cell, then only we can give the fuels, that is hydrogen and oxygen, and apart from that, when we are having no use of fuel cell, we can stop giving the fuels. So in this diagram we can see we are having a source of hydrogen over here and we are having a source of oxygen at the other electrode. We are giving sealing, that is so that the fuels can partially give to the electrodes, or we can say the fuels are directed to the electrodes without any loss. So hydrogen is giving to the one electrode, oxygen is giving to the other electrode. When they combine each other at the electrolytic solution or membrane, they will produce heat as well as some water. A single fuel cell produces the power which results from the area times the current density of the cell times the cell voltage. That is, we can say power is equals to the area multiplied by the current density multiplied the cell voltage of that particular cell. The typical cell voltage under the load conditions, as I have already told in the last slide, it is approximately 0.6 to 0.7 volts, which is too low for practical applications. And hence we are using different fuel cells in a stack. So stack is therefore common practice to put a number of cells in series, resulting in a so-called fuel cell stack, or we can say having a high volts of the fuel cell. And these stacks, when connect two adjacent cells, then these are known as flow plates. So flow plates connect two adjacent cells, also called separator plates or bipolar plates, and when a single plate is used for the anode side of one cell and one for the cathodic side, should have a high electronic conductance and should act as a gas separator between the two adjacent cells. These flow plates contain flow patterns on the cell side to generate an even distribution of reactants across the cell area. On the back side, cooling liquid flow patterns transport the heat to a heat exchanger in the system. The stack power and voltage is obtained by the number of cells times the individual cell power and voltage. That is, we can say the stack power is defined by the number of cells we are using and having the individual cell power, so multiplied by the number of cells. So if we are using 6 cells, we can say the power of a total stack will be equals to the 6 times the power of individual one cell, and similarly for the voltage. The efficiency of the fuel cell stack, that is EFF subscript in FC, the utilization of the hydrogen and the power consumed by the balance of plant components determines the total system efficiency. That is, in the reaction form we can say efficiency is equals to the efficiency of the fuel cell plus utilization of that hydrogen and the power consumed by the balance of plant components. The efficiency gains can be obtained by operating at a high cell voltage, maximizing the utilization of hydrogen, minimizing the flow of air or oxygen which we are using, and minimizing the pressure drop at anode and cathode. Now let's move forward to the next topic, that is the solar cells. A solar cell is a solid state electrical device, that is, we can say PN junction, that converts the energy of light directly into the electricity using the photovoltaic effect. The process of conversion first requires a material, which we are using generally silicon, which absorbs the solar energy, that is photon, and then raises an electron to a higher energy state, and then the flow of this high energy electron is to be used on external circuit. As we can see in this diagram, the photons are directed to the material, that is the siliconic material, and these electrons are the basis of the passage of current which we are flowing from the two electrodes, that is the anodic and the cathodic electrodes, and the holes are released. These are also having some conductors and some negative conductors, that is the N layer, and the back contact, that is the positive conductor, which can be called as P layer, and that is why we are saying it is P-N junction. And we are also providing anti-reflective coating so that these photons which are directed to the material cannot reflect back to the light. As we can see in this diagram, we are using one cell. If more than one cells are connected in series, then we can say module. Like in this part, we can see that more than one cells are connected in series. Then when more than one module are connected in series, as we can see in this part, these can be called as string, and when more than one strings are connected in parallel, they can be called as array of a solar cell. Now the PV cells, that is the photovoltaic cells. These are most commonly made up of silicon and come in two common varieties, that is the crystalline and the thin film cells. As we can see that the crystalline form is again made up of monocrystalline and the polycrystalline, whereas the thin film type is again of 4 types, that is the CDTE, that is the cadmium telluride, CIGS, that is the cadmium, indium gallium selenide, then the CIS, that is the cadmium indium selenide, and the amorphous silicon type. But generally we will discuss the silicon based PV cells. Now what is the PN junction? As we have seen in the solar cells, we are using the PN junction. So it is formed by joining P type, that is the high concentration of hole or deficiency of electron, and the N type semiconductor. N type means high concentration of electron and the low deficiency of holes. Due to this joining, excess electrons from N type will try to diffuse with the holes of P type, whereas excess holes from P type will try to diffuse with the electrons of N type, and hence the movement of electrons to the P type side exposes positive ion cores in the N type side, while the movement of holes to the N type side exposes negative ion cores in the P type side, and this results in an electron field at the junction and forming the depletion region. The generation of current in a solar cell will be known as the light generated current. Involves mainly two important processes, that is the absorption of incident photons to create electron hole pairs, that is again P and N junctions, and these electron hole pairs will generate in the solar cell provided that the incident photon has an energy greater than that of the band gap. However, electrons in the P type material and the holes in the N type material are metastable and will only exist on average for a length of time equal to the minority carrier lifetime before they recombine. If the carrier recombines, then the light generated electron hole pair is lost and no current or power can be generated with these cells. So the collection of these carriers by the P and N junction prevents this recombination by using a PN junction to spatially separate the electron and the holes. The carriers are separated by the action of the electric field existing at the PN junction because of the holes and the electrons. If the light generated minority carrier reaches the P and N junction, it is swept across the junction by the electric field at the junction where it is now a majority carrier. If the emitter and the base of the solar cell are connected together, that is if the solar cell is short circuited, then the light generated carriers flow through the external circuit and no power will be generated. The photovoltaic effect, which is mainly the basis of the combination of P and N junction. The collection of light generated carriers does not by itself gives rise to power generation. In order to generate power, a voltage must be generated as well as current. Voltage is generated in a solar cell by a process known as this photovoltaic effect. The collection of light generated carriers by the P and N junction causes a movement of electrons to the N type and holes to the P type side of the junction. Under the short circuit conditions, the carriers exit the device as light generated current. Now we have studied just the solar cells, and initially we have studied the polymer electrolytic membrane. So we can say for the solar cells is a type of flexible solar cell made with polymers, that is the large molecules with repeating structural units. As we have already studied, the polymer is made up of so many monomers connecting together. So these type of polymers are used in particularly solar cells, and hence we are saying that it is a polymer solar cell. These polymer solar cells include organic solar cells, also known as plastic solar cells. They are one type of thin film solar cells. Others include more stable amorphous silicon solar cell. Most commercial solar cells are made from a refined, highly purified silicon crystal, similar to the material used in the manufacture of integrated circuits and computer chips, mainly wafer silicon type. The high cost of these silicon solar cells and their complex production process generated interest in alternative technologies. Now, what is the basic principle of these polymer solar cells? Like all solar cells, the polymer solar cell converts light into electricity by converting a flux of photons, that is the light, into a flux of charged particles, that is we can say current. But this conversion process is made possible by the combination of several types of materials, all having distinct electrical and optical characteristics, presenting the polymer solar cell stack, but most importantly is the inclusion of semiconductors. The main basic three steps of this conversion process are summarized in brief. The first process is a photon incident on a semiconductor having an energy that exceeds the semiconductor band gap, which excites an electron to an unoccupied state above the band gap, creating an electron-hole pair, that is the EH pair. This electron-hole pair is subsequently separated over a built-in gradient in the electrochemical potential of the solar cell. And finally, this electron and hole, which is already separated, is collected at opposite electrodes and led to recombine after being put to work in an external circuit. As we can see in this diagram, we are having at anode, when photons are directed, then these photons force exciton to separate into some holes and some electrons, and then these holes and electrons are redirected to different electrodes, that is at anode and that is at cathode. As we can see in this diagram, the electrons are directed to the cathode, whereas the holes are directed to the anode, and at both the electrodes, these holes and electrons are recombined to form some energy. So, what we have discussed till now are the types of batteries, the fuel cells, the solar cells and the photovoltaic effect, and next the polymer solar cells. The new photovoltaic energy technologies can contribute to environmentally friendly, renewable energy production and reduction in carbon dioxide emission. The latest advances have shown a great potential for organic solar cells over conventional batteries and fuel cells. Their versatility in production methods, properties and applications looks very promising for the future of solar energy. With this, we come to an end of the unit batteries. We have discussed the basic units of batteries, its classification, fuel cells, the solar cells and the polymer solar cells in detail. Hope you understood the unit. Thank you.